Yo, what's up, everyone? Good morning. Happy morning. Ugh, they're doing like something downstairs. I woke up this morning too, and I was like, ugh. But I closed my blinds. It's all good. Maybe this is just irrelevant info. Anyway, it's Thursday for me. Full disclosure here. Uh, get this done before homeroom. Sorry, it says Wednesday. Okay, this is the worst intro of all time, but we got 3 lessons left. This one, then we have 2 next week, and we're talking about something called the chi-square test. And first, I'm happy because this is funny, but this is actually the first year that I've ever taught this. Um, Last year, they cut it out of the material because they did like a shorter AP. So I didn't teach it last year. And then the year before was my first year teaching AP stats. And we didn't make it this far. So, and actually, this is the last year of AP stats. I think I'm going to talk about that eventually because we're becoming an IB school. So this is the first and only time that I'll teach you or teach anyone chi-squared, which is a shame because I think it's a cool topic. So hopefully you think this is kind of cool. It's going to tie a lot of things together. I always say that when we bring back an old type of graph, but I think that this is really cool. So 2 examples. So it might be kind of a little long of a worksheet, but actually the stuff we do next week is going to be really easy. So I might even try to finish those up this weekend so that I can give you time to catch up before our May 17th review start. Okay, fair enough intro. Let's do this example problem. It says, imagine you open up a large bag of Skittles and you record how many Skittles are in each color in the two-way table below before eating them. So this is kind of standard. There's approximately 60 Skittles in a bag. And you're like weird, so you want to kind of count how many are each color. And you organize it in a two-way table. So we've seen two-way tables a lot in this class. And let's talk about what we would used to do with the two-way table. Two-way tables were a big part of probability, where we would say what happens if we, take out multiple Skittles from the bag. We talked about with or without replacement, stuff like that. But what you need to remember about a two-way table for today is that was when we started creating proportions, okay? And this is categorical data, right? Because if you're a Skittle, we're talking about what color you are, which is not a number, it's a category. So we can turn any of these into a proportion and say this percent of my total bag of Skittles is a certain color. So for A, it just says what proportion of your Skittles are red, right? So what we would have done before is we know that 15 out of my 60 Skittles are red, right? And I think that's 25%, which actually isn't going to be too useful today, but the proportion is 15 over 60. So hopefully that's clear to everyone. And then, what's the probability you get 3 reds in a row would just be this times this times this, as long as it's with replacement. But that is a proportion, right? And we can find the proportion of all of them that are each color. So first it says what proportion of Skittles are red. And then this is new but not difficult. It says if there were an equal number of Skittles of each color, what proportion would be red? Okay, so first, the proportion as far as a percent, think that there's 5 categories here. So if all of them had the same color, if there were sorry, I said that wrong, but if there's an equal number of Skittles of each color, meaning that there's the same number of red and green and yellow, each of them are going to be 20%, right? But what's more important today is exactly how many Skittles do we expect to be red? So you could set up a proportion with, let's just do it, honestly. This is the kind of math maybe you could do in your head, but maybe it's good to talk about. We need what number divided by 60 gives us 20%. So actually, we just need to multiply those 2 numbers together to get 12, okay? So that is our beginning part, pretty simple. And hopefully that makes sense. So in this case, there were 3 more red Skittles than we would expect in the bag. There were way too many green ones, not that enough orange or yellow or even purple. So this is now where we're going to start getting into end of the year stuff. We're going to talk about some tests. We're going to start with a claim. So in the last one, we were just saying that if there were an equal number of each color, what proportion would be red? But now we're saying that Skittles claims that their bags have an equal proportion of each color Skittle. Okay, so this is what we got in real life, but they're claiming that at least on average, there's 12 of each. Okay, so that's the claim. And that's a true claim, right? Skittles would say that they have an equal number of each of the Skittles. Why wouldn't they? I know some people have preferences for them, but actually I was doing a little research before this on Skittles. I don't know why. And apparently people think right now are saying that they're all the same flavor. They just smell different. So maybe they're all just the same Skittle, they're just fragrance different. I don't know. Either way, they're claiming that every Skittle bag has an equal proportion on average. And maybe I said that poorly. Let me reapproach that. Every bag doesn't have to have this 12, 12, 12, 12. But we're going to look for evidence that our bag of Skittles was so off from that that it couldn't possibly be true overall. So anyway, Skittles claims that the bags have an equal portion of Skittles. And it says, describe how you could run a significance test comparing the red Skittles in your samples to the expected number of red Skittles. So using what we have above, what I want you to visualize is that we could run a one sample proportion test. I said that poorly because this is beautiful. What I'm trying to say is like, this is what happened in our sample. 15 out of our 60 Skittles were red. But Skittles claims that 20% or 12 out of the 60 Skittles are going to be red, right? So we could run a significance test testing that claim. We could test that the proportion equals 0.2 or the proportion does not equal 0.2 because we have no way of knowing if it's above or below that value, right? So this is the claim. The claim is that it's 0.2, and what happened in our sample was that it was 0.25. So we could run a whole test testing whether there's a testing whether 20% of my Skittles are red overall. And we would even set up, our Z, the data points is what happened in our sample. The mean is the claim. And then we could even find a standard deviation using the sample proportion, right? And, let me just do that very quickly. This isn't the point of the lesson. This is just to show you something that's possible. 0.056. And even looking at that, it's going to be 0.05 divided by 0.056. So it's going to be like a 0.8 z-score, and it's going to fail to reject, right? So you actually can already see what's going to happen. But what I want to talk about, and the reason I just glossed over that, is that this test doesn't actually test the entire claim, right? The claim is that all of these are going to be 12, that the proportions are equal. There's no preference towards red in the claim. So we could test every single Skittle and get a bunch of different p-values, right? We could do that for 11. We could do that for 18. We could do that for 9. We could do that for 7. We could run 5 different tests just testing whether the proportion is 20%. But that doesn't even test whether all of them collectively are 20%. So I hope that makes sense. That's our setup here. So when you do a proportion test, you choose a single proportion out of your whole data set to run your test on. But what a chi-square test is going to do is it's going to test every single proportion, okay, using a single p-value. One p-value to tell you, are these proportions equal, right? Do we have evidence that the proportions aren't equal because all of these are so far away from it? I hope that setup makes sense. I think I explained it okay. A proportion test only can test one of multiple proportions. So think even like an old, anything we would talk about, like 40% of people think this, 40% of people think that. You could always test the opposite proportion. And a lot of times there's multiple answers to a proportion. And what a chi-squared is going to do is answer them all at once. Okay. So maybe that end was kind of crap, but C says run a chi-square test for goodness of fit to test whether proportions of scales of each color are equal. So we want to include hypotheses, and honestly, for the sake of time, conditions are always kind of similar. We're going to start with the hypotheses, okay? And these hypotheses, and this is really important, are going to be written, okay? And they're going to be exactly what we just talked about. The null hypotheses are all colors of Skittles are equally represented. The alternative is that they're not, right? So think that we're going to run a test here, testing all 5 of them at the same time, okay? And we're going to get one answer. Are the proportions equal, or are the proportions not equal? Because think about this, right? We already failed 15, or failed to reject 15. 11 is really close. And we would fail or reject this thesis depending on which Skittle we chose to test, right? So that doesn't make a lot of sense, right? Just because the yellow, that's weird. Just because the yellow are different, or the orange would be a better example, doesn't mean all of them are going to be different. So that's why we want to do a chi-squared test. So the null hypothesis is all colors are equally represented. The alternative is all colors are not. And the way we're going to do this is we're going to come up with a number called the chi-squared statistic, okay? And maybe now's a good time to bring up the formula sheet. This formula sheet, you could even Google it, is the AP Statistics formula sheet. And the front page has kind of a lot of crap until you get to here. It's really useful. This has all your standard deviation formulas. And then on the end, the majority of the formula sheet is dedicated to your z-score, your t-score, and our final chart, we've made it to the end, the chi-squared, okay? So I'm gonna have this whole thing ready for you, but have this printed out. But what we're gonna do today is use the chi-squared distribution, okay? And there's a second formula here that's important. And it is the chi-squared statistic. It's like an x squared. And it's one of those things, it's going to be really easy, honestly. And I think a lot of people have maybe done this in bio, maybe even just the Health Academy. It's kind of common. But all you're going to do is do observed minus expected for every single data point, squared, divided by expected. Then you're going to add them all up, and that is going to give you your chi-squared number that you plug into the chart. So it's actually a little easier than you might think. I appreciate you guys for bearing with me, because I don't know if this has been the best lesson. But observed is going to be what happened, right? When I counted my Skittles, 11 of them were purple. The expected number for every single Skittle was 12. We're going to square that. And again, we square numbers in statistics so that positives and negatives don't cancel each other out. And then we're going to divide by expected. And the logic there is that we want to kind of scale this, right? So think that this distance was 1, but we want the context, right? We're talking about 12s. Hopefully that makes sense. The reason is, like, think that I could have picked 600 Skittles, and if we're 1 away in a 600 batch of Skittles, that's not nearly as significant as 1 away from a 12 batch or a 60 batch of Skittles. So that's why we're going to divide by expected. But here's the tedious part. We're going to do this for every single data point. So here are my red Skittles. Here are my green green Skittles. Here are my yellow Skittles. And here are my orange Skittles, okay? And the good news is this is like kind of like the only thing you have to do. You're gonna take every single type of category you have. So the longer the two-way table, the harder this is gonna be. But this is a 5-section two-way table. Subtract away the expected and divide by expected. So do this on your own. I'm gonna speed through because it's not like the hardest calculator work, I don't think. And even though it's all of that math, the number you get usually isn't going to be too big. Okay. So first, let's talk about how you can kind of look at these logically. This value you want to be as small as possible. Think that if this value is extremely small, that meant that all of your data points were really close to what was expected. If this number is really big, that means that everything was far away from what's expected. So think that you want a low value if you want to say that the null hypothesis is true. A low value indicates that all the data was actually really close to what's expected. And all we're testing here is, are they equally represented like the claim says, or are they not equal? So that's step one. And then the second thing that we have to do very quickly is the degrees of freedom. I'm actually to look this up right now. Okay, yeah. So the degrees of freedom is going to be the number of categories you have minus 1. And I know this year I didn't really explain degrees of freedom that well overall, but I don't think it's a big deal. Just know that there were 5 categories, so degrees of freedom equals 4. The more categories there are, basically, or the higher this number, the more lenient you're going to be, right? Because if you have a lot of values added together, you kind of expect this value to be higher. So the lower this is, the stricter it is. The higher this is, the less strict it is. So these are going to be your 2 inputs into the chi-squared chart. Here it is. It looks really similar to the t-distribution. And I'm not even really going to explain the graph as much this time. Let's just get into how to actually really do it. But here's how we're going to look. We're going to look for our degrees of freedom. In this case, it was 4. And then we're going to look for where my 6.66 falls. So it falls in between 5.99 and 6.74. And this is just like how we use a t-distribution. That means that our p-value is in between 0.15 and 0.2. Okay? And just looking at this chart, hopefully it makes sense. Think that if we had like a value of 20, then the probability that they're still equal is really low. Okay? This value is small, right? Most of my data was actually pretty close to the center, and we didn't really have a high number of proportions. So we're going to get a pretty high p-value. And p-values always mean the same thing, because I know this is something that a lot of students struggle a bit with. But know that the chi-squared is still a test. So we have confidence intervals and we have tests. And a test, you always compare to a significance level, which in this case we'll say is like 0.1. And because this value is big, that means it is still possible that all the Skittles are equally represented, right? We didn't really get super far away answers, okay? So we don't have conclusive evidence to reject the null hypothesis. So we're gonna fail to reject. And again, I've talked to students who find this hard. High p-values mean it's possible that this is true, so we fail to reject. Low p-values mean that this is impossible, so we're gonna reject it in favor of this. And again, that might be unsatisfying because like my Skittles were different than 12, 12, 12, 12, 12, but they weren't different enough to reject it. And a note on, tests in general, we don't say we accept this. We just say we fail to reject it because we didn't find evidence this was true, right? In fact, we found evidence that it's likely not true. We didn't find enough evidence to reject it. Okay, excellent. I think we're doing pretty well on time. Hopefully you guys understand the setup. We're going to do a second example, honestly. But I just want to talk quickly. Can you have a confidence interval using chi-squared? And the answer is no. And I just want you to think that we are combining a bunch of proportions. So there is nothing for us to say plus or minus some value when we're talking about all the Skittles, right? So when you do chi-squared, if you want to do something with an entire like a bunch of proportions in a row, a significance test is kind of all you can do. And that's why like significance tests are so useful. Because like in my opinion, the confidence interval is better for like a proportion, a normal mean. It gives you kind of a cool answer to say we're 90% certain it's in between these values. But when we combine a bunch of proportions, all we can do is reject or fail to reject a claim about all of them entirely. All right, we're gonna run the second example so that we can really get into the math, make sure we're good with it. It says that roulette is a casino game where a wheel with the numbers 0 through 38 is spun and a number is selected by where a ball lands. I just put that explanation. I think you guys know roulette. And it says in a standard roulette board, 18 numbers are black, 18 numbers are red, and 1 number is green. And a casino is accused of having a rigged wheel. So the owner spins it 100 times to test it. So the most important thing for a chi-squared test is to recognize that there's basically 2 sets of data you're comparing. What actually happened, which is this, right? Think that they spun the roulette thing 100 times and kept track of their results. But we're comparing this to what would be expected with a normal roulette wheel. So you don't have to do this, but you're really comparing 2 different two-way tables, always. And you just have to find the values. But think, if we spin it 100 times, and it's just like early in the year, residuals, observed minus, observed and expected, right? This is what happened, and we're trying to figure out what would be expected. And I wanted to do this example because in the first example, all the proportions that are expected are equal, right? Because we were claiming that all the Skittles had the same proportion. Here, that's not true. The expected isn't 33, 33, 33. What's expected is this percent. So this question is actually harder maybe than I wanted it to be. But think that in roulette, and there's actually 2 ways to play. I did some roulette research as well. One of them seems kind of like BS, honestly. But think that there's 39 options. 18 of them are black, 18 are red, and 1 is green, 0 through 38. So these proportions are going to be expected. And then if we want to figure out what's expected with 100 rolls, we're just going to multiply them by 100. Okay, so maybe that could be difficult. I even skipped reading this. It says, if the wheel is spun 100 times, how many times do you expect it to run on these? The only way to know is to find the proportion first. So like maybe you only know roulette from like David Dobrik, always winning. The way that roulette works is that getting black or red, it's not actually a 50% chance because there's like the 0 is possible. So there's black and there's red. So you can choose one of these to have a decent 50, like almost 50-50 shot, but it's not 50-50 because there's kind of this extra proportion. So that's how the house always wins in roulette. But now we're just going to multiply these by 100, which just means move the 0 over. Like this. No. 2.56, 2.56. Good. Good. So this is what's expected, and this is what happened. So now if we want to run a chi-squared test, this kind of test is satisfying. Like, we should write the hypotheses, but right now I'm just focusing on the math. This is fun because all we're going to do is observed minus expected squared over expected. So every number is laid out there for you. And think that if we get a really big value here, that means that the roulette board is rigged, because all of these were sufficiently far away from what's expected, right? And this one might fail. Who knows? It looks like some of these values are pretty far away. Okay. I'm going to speed through the math here. The calculator work, I mean. I'll just write the smalls. That wasn't that far. When you divide by this, it's going to make a big difference, keeping the numbers relatively small. So if I'm looking at these numbers are looking pretty similar to what we got in the last test. So we might be moving towards another fail to reject. We're getting 9.1856. And now the degrees of freedom is just going to be the number of categories you have minus 1. So it's 2. So like, remember when we did the t distribution, which is just on the other page? Most of the time we were down here. When you do chi-squared, you're almost certainly going to be over here. And if you're not, you're screwed, because that means that your table has like 25 categories, which I would never make you do. 2. And here we go. We're in a, so, and you know, this is my first time teaching it, so I'm kind of learning with you a bit. 9 is looking like something that might reject sometimes. We're at 9.18. And that's really close to 1% as a p-value. Okay, so we'll keep it consistent in this one and do a 10% significance level. But 0.01 is less than p, which is less than 0.02, which we can say is less than 0.1. So we're going to reject. And I went through that end quick because I think there's another long video. But hopefully that makes sense. So this would be our significance level. You still need a significance level for a chi-squared. And you still have to estimate your p. Maybe that's worth talking about here. That's a limitation to the charts, because we don't know exactly what that p-value is, but think that it's probably like 0.011. You know what I mean? 9.18 is like right there. So that's low enough that this roulette person would get fired if the casino did this, because they're getting green all the time. So hopefully that makes sense. I appreciate you guys. I thought it was a good lesson. And 2 more lessons very similar to this next week. Alrighty. Appreciate you. Proud of you.